All right, we're continuing with the curve sketching example problems. This is the 12th example problem we're going to work. In this video, we're going to sketch this function here. All right, step one, the domain. So we've got two odd roots here. This is the third root of x to the fifth, or the third root of x to the fifth, right? So this is, you could write this as the third root of x to the fifth, the third root of x to the fifth, or the third root of x, all of that to the fifth. But regardless, the main potential domain issue comes from the root. But we know that for odd roots, you could input any real number into an odd root, and you're going to get a value. So here, the domain is going to be all real numbers. All right. The range should be all real numbers as well, but we'll come back to the range once we sketch the graph. Okay, next, intercepts. Let's look for y-intercepts. You set x equal to 0. Okay, so when x is equal to 0, y is equal to 0. So the origin is an intercept. It's going to be an x and a y-intercept. So now let's set y equal to 0 and solve for x. Okay, so we've got x to the 2/3 minus 5 times x to the 2/3. Is that right? No, that's not right. X to the 5/3 minus 5 times x to the 2/3. Okay, and we're going to store this as e. All right. Okay, so now we want to solve for when e is equal to 0 for x. X is equal to 0 or x is equal to 5. Right? So x is equal to 0 or x is equal to 5. That's the two x-intercepts. Okay. So we're going to put as the axes minus 10 to 10 on the x, and then same thing on the y. So minus 10 to 10. Okay. Now, so the origin is an x and a y intercept, and then 1, 2, 3, 4, 5 is an intercept. Okay. Now let's check for symmetry. So is this an even function? Y of minus x is what? So, okay. Well, okay. Well, let me see if this will work. So with x is equal to minus x, will that work? No. Okay, so minus x to the 5/3 minus 5 times minus x to the 2/3. Okay, what do we get here? Minus x to the 5/3 minus 5x to the 2/3. Okay, this is not equal to the original function. Okay, what about an odd function? Is this an odd function? What is minus y of x? Minus y of x is minus x to the 5/3 plus 5x to the 2/3, and this is not equal to y of minus x. This is y of minus x, okay? So it's not odd or even. What about, is there periodic symmetry? So is there some number p such that y of x plus p is equal to y of x? No, there's not. This is not a trig function, not an inverse trig function. This is not a hyperbolic function. And so unless, for all of the, if we're dealing with a type of function that a typical function we've dealt with in algebra and trigonometry, then unless it's one of those that we know is periodic, then it's not going to be periodic. So, okay. Next, the endpoint behavior. Let's take the limit as x approaches each of the endpoints of the domain of the function. Okay. So, limit as x approaches negative infinity of e is negative infinity. Okay, what is the limit as x approaches infinity? This is equal to infinity. Okay, that's the endpoint behavior. Next, let's get critical points. Starting with the first derivative. Okay. So let's take the derivative. All right. So let's solve for when this is equal to 0 for x. X is equal to 2. Now, we also know that we can see here that the first derivative doesn't exist at x is equal to 0. So x is equal to 0 and x is equal to 2. All right, and so we know 0, 0 is one of those points. And then what is the function evaluated at 2? So e with x is equal to 2 is minus 3 times 2 to the 2/3. Okay. Now the second derivative. So d squared. All right. X is equal to 0 is gonna be 1 point, but let's see if there's other points. X is equal to minus 1, okay? So x is equal to 0. It didn't exist at x is equal to 0, and then at x is equal to minus 1. So you've got 0, 0, and then minus 1. And then if we come minus 6. Okay. So let's plot these points. If we come here, what is this? Minus 4.76. So 2 and then minus 4, 1, 2, 3, 4.76, about right there. Okay. Then minus 1, minus 6. 1, 2, 3, 4, 5, 6. About right there. Okay. Okay. Next, what we want to do is we would, the textbook talks about how now we want to look for vertical asymptotes. If we didn't know the function, if we were just analyzing this blind, then what we would do is we would come to every single critical point of the first and second derivative and just take the limit as x approaches that point from the left and the right of the function, just to see how the function behaves. If it goes to infinity and for any one of those limits, it's a vertical asymptote. But even if you were if you were analyzing the function blind, you could, for all of those critical points, you could take the limit as x approaches that critical point from the left and the right and see what the function does, what the derivative does, what the second derivative does. You would analyze all of the critical points that way. But we don't go into that level of detail in a typical calculus course like this. The first thing is that we know that we're not going to have a vertical asymptote with a function like this. Vertical asymptotes are like when you're dividing by 0, or for certain trigonometric functions, or for like logarithms at the endpoints, things like that. Here we know we're not going to have a vertical asymptote. However, what we want to do though is, if we have a critical point associated with the first or second derivative critical point that's associated with the first or second derivative not existing, except for not including an endpoint, then we want to analyze that critical point as far as the limit as x approaches that critical point in terms of the first derivative and the second derivative. So, well, okay, this function is continuous everywhere, so we don't need to take the limit as x approaches 0 of the function, because we know that limit's going to equal 0. But so again, so the first derivative exists at x is equal to 2 and x is equal to minus 1, but the first and second derivative don't exist at x is equal to 0. So let's do this. Let's say, what is the limit as x approaches 0 from the left of the first derivative? Okay. So what we'll do is, let's get this and we'll save that as D. Okay, now let's get this and we'll save that as, we'll call it C. Okay, now let's take the limit, well actually, okay, the limit of the derivative with respect to x approaching 0 from the negative direction, infinity. Okay, now what is the limit as x approaches 0 from the right of the first derivative? Negative infinity. Okay. What is the limit as x approaches 0 from the right of the second derivative? And what is the limit as x approaches 0 from the left of the second derivative? Okay, so we take this, replace it with C, infinity. Infinity. Okay, so now this is going to give us some good information for drawing the curve around this critical point where the first and second derivative don't exist. We don't need to do this for the other critical points because we know this is associated with a 0 slope. This is associated with a 0 concavity, so it's going to probably be an inflection point. Okay, but let's do that though. Let's do that. Let's analyze the regions of the increasing, decreasing regions. So x is equal to 0 and x is equal to, so let's do this. X is equal to 0 and x is equal to 2. Those are the only 2 points where the first derivative can change signs. So let's do this. So we've got the derivative with x is equal to, let's put minus 1, 5. So increasing in this region. Now what about when x is equal to 1? Decreasing in this region. Okay, what about when x is equal to 3? Increasing in this region. Okay, let's do concavity. So we've got x is equal to 0 and minus 1. Okay. So we've got curve C with x is equal to minus 2. So concave down. All right. And then now with x is equal to minus 0.5, concave up. And then now with x is equal to 1. Concave up. Okay. So now this, do we have local maxes or mins? Okay. How do we test to see if we have a local max or min? Well, you can use the first derivative test unless it's you can't use it across a discontinuity. You can't use the first derivative test. But we don't have any discontinuities here. This function is continuous everywhere. So each of these critical points is not a discontinuity. So we can use the first derivative test. Does the first derivative change signs across this point? Yep. It goes from increasing to decreasing. So this is a local max. Okay, here it goes from decreasing to increasing. This is a local min. Okay, inflection points. What's the rule for inflection points? The curve has to be continuous. Okay, you can have a local max or min at a discontinuity. You just can't test for the local max or min using the first derivative test. You can't have an inflection point at a discontinuity. But we don't have any discontinuities, and so we can use to test for an inflection point. We just see, does the second derivative change signs across a critical point with respect to the second derivative? It does here. This is an inflection point. It doesn't here. This is not an inflection point. Okay. So so we need to draw the curve now. Let's look at this point here. This critical point here with respect to the first and second derivative, but the first or second derivative didn't exist here. But we learned that the first derivative approaches from the left, it's approaching infinity, and from the right, it's approaching negative infinity. What does that mean? Okay, well, that's telling us it's going to be a vertical slope. So we're not going to come in here like this. Well, or we're not going to come in. We want to make sure that we get a slope going straight up and like a line kind of going straight up and down right when we get into this point. And all this means here, so let's draw that. Okay, like that. And all this is saying is that if you're coming from the right, the limit is approaching, or from the left, the limit of the derivative is approaching infinity. It's vertical. But if you're going in this direction, it's negative infinity, because you can see we're going to be coming in this way to positive, and then we're going to be coming out this way to get to this point. So you see the slope is positive coming in from the left and negative coming out from the right. But in either scenario, it's a vertical slope. You see? Okay. Now, when this point here is, what was this point? This was a local min. Okay? But it was a local min where the first derivative is equal to 0. So we're going to have a horizontal line. This was a local max, but it wasn't associated with a horizontal slope. It was associated with the first derivative not existing. But again, what this is going to be like this. We talked about you can have a local max or min just with something like this. Like that's kind of like what the absolute value functions are like, right? That's a local min, but the first derivative doesn't exist there. It's not like it's equal to 0. Okay, so let's like that, and then like that. Okay, and so based on drawing this, we expect to the left of this x is equal to 0, we're concave up. Yep. And then to the right, we're also concave up. And then we're going to be concave up all the way to infinity here, like that. Okay. And then here, we're concave up, but then we have an inflection point. We switch to concave down, like that. You see? So as x approaches negative infinity, let's come back here. As x approaches negative infinity, the function goes to negative infinity. As x approaches positive infinity, the function goes to positive infinity. There's no symmetry. We've got the x-intercepts at x is equal to 0 to x is equal to 5, and there's only that one y-intercept at x is equal to 0. Okay. What else? We've treated this point here correctly where it's a vertical slope. And I mean, we could have, as far as getting the concavity approaches infinity as well. I guess the vertical slope means that, a horizontal line has no concavity, a vertical line has infinite concavity, I want to say. But I think this is plenty good enough just to give you a general idea. Okay, we've got this critical point here, here, and here, where this is an inflection point. Here the slope is 0; it's a local min, and then here we've got this vertical slope. Concavity is down here, then up all the way to the left of this point. Down, up, up. Okay, what about the increasing, decreasing? The function is increasing all the way up to 0. Then it's decreasing all the way up to 2. And then it's increasing for the rest of the function. So there you go. Now, what about the range? Well, we can see the range is going to be negative infinity to infinity. Right? You can get all possible values of y are covered. All right, and that's the sketch of the graph.